Hi, my name is Jay Nelson. I have my code up on DualMark on GitHub, and this is part of the epoxy library, which is Erlang patterns of concurrency. The library has multiple other things in it, but today we're going to talk about a new feature, which is concurrency Fount. The code is up on master now. It's not tagged yet for 1.1, but it will be tagged for 1.1 when it's fully ready. So if you're currently using epoxy and you just use master as your package manager include point, you've already got it if you don't know it. So beware. You should be using tags. So basically, a concurrency fount is like a water fountain of processes. It's a reservoir that contains pre-spawned processes, and you talk to the process reservoir as the API to get workers for your application. So when you drain the reservoir, it's refilled through a regulator. And that's the back pressure technique for controlling how much concurrency you can actually consume. Rather than spawning and just spawning until you run out of memory, there's a control mechanism to limit the amount of spawning and still allow you to handle spikes. So it's a principled approach. I use behaviors so you can implement in the workers an actual receive loop with behavior. And so you're not just giving them functions and letting them run willy-nilly. So here's a basic task. I have client requests, and I want to service them. And using OTP, a smart Erlang programmer, you implement a gen server, and you're done. Then you start to get multiple requests. They stack up on the mailbox. You can still handle them fairly rapidly. If the number of requests starts to build up and the time to give a response takes longer, then there's latency introduced in this process. So being a smart OTP programmer, you use no reply in your gen server. You spawn a process as a new pit, let it crunch away on the thing that takes a long time. You reply back, no reply to the request, and then when this guy's done, he replies back to here, and so bypasses the gen server bottleneck. That works great until you get a large spike of requests, and then there's 10,000 messages in your queue, and latency comes back again. You've got one worker per request, you've got memory and CPU pressure, and if you don't cap the number of processes you have simultaneously, you could end up consuming all the memory or all the CPU or crash the VM. So I introduced Concurrency Control, which is another pattern in the epoxy library. It uses ETS tables so that any process anywhere can increment and decrement, and then you can have a cap that's concurrently accessible. If you were to put the cap in a gen server, you'd serialize it, you end up with a bottleneck in this gen server again. So epoxy tries to get around serialization issues by adding concurrency via ETS table metadata. In that case, when you reach the limit, you can either refuse to run or pause. But concurrency Fount is a different approach. Rather than use a fixed cap, it's actually going to dynamically adjust the availability of concurrency based on how much you're consuming and how much CPU and memory you have available. Not memory so much, but CPU. So back to our problem where we get a big spike and we've got our queue of messages. We've got bursty traffic, and we're spawning responses. We're going to get bursty CPU. 100 processes get spawned, then nothing gets spawned, then 1,000 processes get spawned. And that churn, when you spawn that many processes under load, actually impacts everything on the machine. And in a typical system where people are doing things like that we're like sending a text message. You send it to the server has to find a connection, send it through that socket, wait for the socket, and then reply back that it went through. You try and eliminate that latency and let another message go through. You find out that the background processes that you're handing off to the spawns, some of them take a long time, some of them take less time than the spawn actually takes. If it's a very fast, like increment the next table and continue on, your code ends up in a way that you have these quick little tasks, and they would benefit if you had pre-spawn processes rather than doing a spawn on every work task request. So everybody that comes from another language says, oh, I know about this, worker pools. Worker pools is a solution for pre-spawn processes that do the work for me. And I'm now going to do a flashback to Erlang Factory, San Francisco, 2015. Anthony Molinari from OpenX, his topic was how to pick a pool without drowning. So he said, let me see, there's a lot of pools out there. So he searched on GitHub for process pool, he got 12 results, resource pool, 3 results, worker pool, 18 results, connection pool, 19 results. And then he knew about 7 other pools that didn't show up in his search results. And he tried to whittle it down, and in the end, he had these as his final list: pool boy, pooler, gen server pool, disp count, gproc. And these, because he was trying to limit the list, had problems that he wanted to whittle it down because of the documentation or stuff. But we've used worker pool. That's common. Inaka is owned by Erlang Solutions now, so I should put a plug in for that. But worker pools are a dime a dozen. There's a million of them out there. And most of them have different issues that cause failure problems. And so that's what you have to watch out for. It works fine when you plug it in, and it works fine until it doesn't work. And then generally, a worker pool is catastrophic. And I'm going to explain why that is. So let's say you decide worker pools to the rescue, and I'm just going to do a simple one. I don't want to use an existing library. I just have an application. I'm going to have a supervisor, and it's going to have 20 workers. So now I have a fixed number of pre-spawn processes. The supervisor spawns them on startup. They're around forever. If one of them goes down, the supervisor will restart it. So I don't have to really write any code to manage a fixed number of workers. Well, okay, so that was easy. But now I have to actually send a message to one of the workers. So how do I choose them? I don't know their names. They're just PIDs on a supervisor. If I start querying this supervisor, that's a gen server, and it's going to be bottlenecked. So I get smart. I name all of them and put, worker 1, worker 2, worker 3, and then I register the names, and then I ask the registry which ones are there until there's none there, and then I pick one randomly or round. Well, so I said load balance. It's a little more complicated, but this is simple, right? So it can't be that hard. Then you find out, well, I've got more work than the number of workers. I only have 20 workers, and I've got 100 tasks. And I message, let's say I round robin, I choose in my load balancer. I've got 1 task running and then 19 tasks on the queue, the mailbox for each of those workers. One of the workers trips, falls down, 19 tasks disappear. They're not anywhere else because I sent them there, and they just disappear. So I get a little more advanced. I'm going to add a task queue, and I put my messages in the task queue. The workers pull from there. Before they're done, they check, is there anything there? They pull. That gets a little more complicated now because my task queue has to be bounded. And if the task queue goes down, I lose 1,000 of them instead of just 19, But you wave your hands until there's issues and there's details, and then finally, catastrophic failure. So here's the advantages of a worker pool. You get a typically fixed amount of concurrency. They're supervised on replacement, so that's good. It means they're always around. This is good and bad. You can just send a message to it, or you could send a function to it, and it could execute that function. And so people tend to do that. Not sure what I need the workers for, but I know I need the workers. I'll just pass a function to them. I'll write a new function when I need to pass. Now you don't know what they're running anymore, but it's convenient, so it works out pretty well. But they end up, now when you're debugging, you have no idea what any worker's doing because they all look the same, but they're doing different things. They're long-lived, so there's no latency when you start a task. And hopefully you picked a library rather than rolled your own. After you started getting into the issues, you say, okay, fine, let me take one of these. Since it's a library, it probably has an API that I can replace, and so if this library doesn't work, I'll switch to the other one. That's not quite true, because each one builds slightly differently, and you have to initialize it, and so on. So they're not as replaceable as they seem. And you have to deal with this per worker issue. It's convenient in the beginning if I have short tasks and long tasks, and I round robin. Some workers will stay busy for a long time. Other workers might zoom through 6 tasks from their mailbox quickly. That just balances out and disappears in the noise, and you don't notice it. But if you get too many tasks, it builds up on everybody, and it builds up worse on the long-run task. So you have to find a way to avoid the long-running task. So the plus is we've got predictable CPU usage. Our workload's spread. Plus or minus, we can use the mailbox. It's convenient, but then we lose things if we did. This is a big negative. Once I decide I'm round robin or random or whatever, and I give a task, and it's busy, and it's on the mail queue, and everybody else is free, I can't pull it back and give it to somebody else. It's committed, and there's no way to uncommit from the mailbox. So now you have to build a second mechanism if you want to uncommit, and then it's getting really complicated. The issue we ran into, which was totally unexpected, throwing random functions to the workers, those functions called third-party libraries, 2 different third-party libraries were clever because they knew what they were doing and used the process dictionary. Never use the process dictionary, but I know what I'm doing. Don't ever use it in a library that somebody else is going to use because you don't know what they're going to combine it with. 2 different libraries collide on the same key, crash your worker, and you'll never find that. It'll happen once every 3 months or 6 months or whatever. So now you have a very advanced worker pool. Before you free up a worker, you erase the dictionary, you do a garbage collect, you hibernate, now at this point you've got more latency than if you had spawned in the first place. So what's the point? We were trying to save latency there. This staleness can cause fragmentation in GC. If you have a lot of short tasks, that impacts things if GC is running. There's no back pressure. When you're stuffing things on a mailbox, nobody tells you, hey, there's 10,000 things here. I mean, there is a built-in one, but when you're farming out to workers as fast as you can, that slowdown by the VM is minor. So in advanced pools, you end up with the shared task queues. Super advanced ones, you have worker decay, randomly decays and replaces. I implemented one of those for Cassandra. It's called Elysium, if you look for that. The happy afterlife after Cassandra dies. And forced replacements. Failure mode, though, the supervisor launches replacement workers. Turns out that sounds like a great idea, but when you throw a function to something and it fails, you don't retry it the way you do other things. So it's pointless to restart it with supervisor and restart it with init args. So you're just restarting an empty worker. If you get multiple failures, the supervisor gets overloaded. Then if they get repeated, the supervisor crashes. Then the crash takes down your application. Then it's game over and you're rebooting and it's a mess. It's really bad. And your log file is so full of all these crash restarts that you can't find the trigger. So if you eliminate the supervisor, and that solves your bottleneck problem, but now you can't replace the workers because they're gone and nothing replaces them. So you'd have to build a supervisor out to the side then. So these sort of bottleneck issues are pervasive in naive implementations. And the supervisor really only function is to limit the pool size. load balancing is hard, and what you do is you assign tasks only when the worker's idle, so now you have to manage who's idle, who's busy, and then they have to pull from the queue, and it's just another mechanism. It's really complicated. Concurrency Fount tries to remove the supervisors, have a clean pull from the reservoir, and independently refill the reservoir. So now there's no dependency between the workers working, the reservoir mechanism, and the refill of spawning, pre-spawning. So what I'm doing is pre-spawning, sitting there idle, waiting to be pulled, and then replacing them with idle workers. So they're one-use spawns. So it takes as much CPU and effort as if you did a spawn every time. But you've amortized the latency of the spawn to do it when you're not busy, hopefully. And then if there's a spike, my worker pool might be this big, but a reservoir pool, I can make it extra big so that a spike can be 10x, but then it replaces slowly, so I can recover over time. And note here, I put multiple founts feeding one application. I can categorize my founts. So I might have a fount for quick tasks and a fount for long tasks, or a fount for database connections on a NIT. They open a socket and wait with the socket already open, so you can adapt your categories of concurrency. So I've one reservoir per category. You limit spikes, and you have single-use process. As soon as you get one, you use it up, you throw it away. It dies. No garbage collection if you're good at this, and so it saves a lot overall, even though you're keeping more spawn processes than you need. So there's a little bit of memory usage all the time, even when you're idle, but you'll never go beyond your max memory on pre-spawns. Inside the reservoir, the idle unallocated processes are all linked to the reservoir. So if you kill the reservoir, they all go away. So we use direct linking for that. But when you get a PID from the reservoir, it's unlinked. So now it's free. It doesn't have a supervisor. It's not linked to anything. There's no bottleneck. If you need it linked, you can link it yourself. If you need to monitor it, you monitor it yourself. If you want to supervise it, you can stick it somewhere else and have it be supervised that way. So we don't need a supervisor because it shouldn't fail when it's idle. Like, it should init and have a process. If you can't get that far, you're still debugging. Once you task it, now it's not connected to the reservoir, and so it's not going to cause issues for other workers or the reservoir itself. Allocation always returns you one PID or a list of PIDs. It unlinks it, as I said. You can either get a PID and then do things with it, like monitor it and then send it a message, or you could just pass a list of messages to the reservoir. Let's say I open a TCP socket for SSE, and I get 100 SSE objects. I collect them in a buffer. I just send 100 messages to the reservoir in one function call. The reservoir takes each of those messages and just gives them to 100 PIDs, unlinking them, and then returns you the list of 100 PIDs. So you've tasked them, they've spun off, started, and you've gotten your PID list back. Then you can decide whether you need to keep track of them or throw that away. If you want to monitor it and link it, then you get a PID, do what you want before you message it. And if you're just like, I need 100 PIDs, let me stick them in ETS and put them on a key, you can do that too. You don't have to task them. But they're sitting in a receive loop on idle. When you consume them, that's what triggers replacement. The reservoir is done as slab allocator. So there's a slab of, let's say, 100 processes, 20 deep. So then I can take a spike of 2,000 without having to spawn anything. If you pull off 2 processes, I don't replace them. But once a slab is gone, then the regulator gets a message to replace the slab. So now the regulator is working in chunks of efficient spawn size, and it actually creates one slab every 1/100th of a second. Right now, that's the regulator mechanism. ultimately, the regulator is going to be a behavior, so you can plug in your own governor as to how quickly you refill the reservoir. So that you would be able to use information from the rest of the application and the environment to adaptively change the regulator to control dynamically how quickly you get new spawned. So here's sort of a message diagram mixed with an architectural diagram. When you use the epoxy concurrency fount, you're actually implementing an instance of a supervisor and plugging it into your supervisor hierarchy for each category that you need processes. That creates a rest for one regulator and reservoir. If the regulator goes down, the reservoir is killed, a new regulator and a new reservoir occurs. So the regulator is there before the reservoir so that on a knit, the reservoir fills up by using the regulator. So it actually fills up slowly in the very beginning too. So you might have some startup synchronization, but it maintains a consistent regulation all the time that way. And as soon as I use up a slab, it tells the regulator supplies a whole slab. So if my slabs are 100 wide, then I have 1/100th fewer messages from the regulator than I do from client requests. I could stretch that out to 10,000 and make it only 5 deep. I could make it 3 and 10,000 deep. It comes into the regulator being 1/100th of a second. So by making short slabs, I can slow down the regulator. By making long slabs, I can speed up the regulator in terms of refill. Basically, that dictates the size of a spike and the latency on refilling. And we're efficiently managing the slabs because when you ask for PIDs, if you ask for a slab full of PIDs, I'll grab a full slab instead of the head of the fount. So if you know you always need 10 processes at a time, make your slab width 10 and 1,000 deep, and you can just grab 10, 10, 10, 10. It'll be really efficient. The spawning cost doesn't impact client requests because the regulator is running as a separate genFSM than the client requests are being handled by the reservoir. So we're interleaving client requests and spawns, whereas before it was in line and that was adding to the latency. And yeah, I said we're messaging full slabs. So you can get one or more processes as a list. You can task one or more with a list of messages. Built into the API is a retry. It can be based on repeating 5 times and with a slight delay. You can add a timer, or I don't think it's there now, but it will have a continuation function. So you can retry based on a dynamic back pressure algorithm. So if your repeater timer fails, you get back an empty list, and then you, as the application, can decide what to do when you can't get concurrency. And then you can get the status of the fount and some timing. You can exit how quick, on average, how long is it taking to spawn slabs, and so on. There's also the option to add a gen event, one gen event, and register it with one reservoir. You could use the same gen event for multiple reservoirs, but each reservoir has one reference to a gen event. And by default, that reference doesn't exist, so it doesn't notify anybody. But whenever a slab of PIDs is added, it notifies the gen event. Whenever the reservoir is empty and somebody says, give me a PID, it notifies the gen event. Whenever the regulator reference is changed to a different regulator, if you dynamically try to swap the regulator, it'll notify the gen event. If an unknown message arrives, in case I'm still debugging, I can get it through a gen event. And when you stop the reservoir, it'll send a gen event. So now you can hook it up to PubSub and see when important events are happening and see if the frequency of failure on the reservoir is getting too high. Maybe you should adjust the parameters or something like that. And you could dynamically do that if you swap the regulator then dynamically. So here's an example that comes in the library. Tried to think of the clearest, simplest example I could come up with, and I happened to be looking at somebody else's hex dump code at the time. Hex dump takes a block of data, chops it into fixed size blocks, prints it out as hex, and gives you the text version as well. So I thought, why not take the data, give it to a loader process, which chops it to 32 bytes at a time. And each line goes to a different formatter, and then a collector receives all those messages and prints out the hex dump. So now I can do a parallel hex dump. I'm using Fount workers for this entire graph of processes. This is 60% of the actual code in the example, so it's mostly here. I just wanted to highlight the important things. So when you create a Fount, it's a behavior. So you have to do a behavior with an init, start PID, and send message. Because when you initialize it, I might have some internal state that I use to seed the PIDs as I'm spawning them. Whenever the reservoir regulator wants to create a new PID, and it does, in a tight loop, 100 PIDs spawned, it calls start PID on my behavior. In there, I can do whatever I want and hand back a PID. But Concurrency Fount's library itself has a spawn worker which does the right thing if you just have a module. It spawns it and then returns the PID and links it. The key is it has to be linked to the reservoir. So if you write your own, you have to link it to the reservoir. And I just supply my behavior module. And I have a function called formatter, which is going to receive the data. If I do a send message, I can use the built-in concurrency Fount send message. It sends a message, but it returns the worker, not the message. If you just use send message, you won't get the right reply. Format data is tasking a PID with a message. So if I get a block of data, I have a Fount, I have my block of data, and I have a collector. I issue the message, load data with hex collector is the PID that's going to be collecting the results. And I task the PID, so it's going to send the message to a PID, unlink it, and then send me back the PID. So now it's got the chunk of data, and it's already started chopping it as I'm getting the reply back of which PID it is. In my receive loop, I've created a receive loop called report data, and that receives the hex dump lines at the end after I've collected everything and prints out my nice table. So inside this function report data, I'm going to receive and collect line by line. And I'm going to receive a whole batch of lines that is the answer to the hex. And then I'm going to format neatly and print a table. So I've got two functions here, format data, report data. In my worker receive loop, a single message arrives after unlinking from the Fount. It doesn't matter whether in my original diagram I had multiple. I have a loader, I have a formatter. Those are both going to be workers, but using different clauses of the receive loop. So that I can have one receive loop, one implementation, one behavior, and I can see how they coordinate by looking at one receive loop. So, and when we started it, we called the function formatter with no state because I didn't need the state. So this is the fan, one loader and format, one collector. Each of them will respond to only one type of message, either a loader message or a format So if we get the first stage data loader message, remember it was load the block of data at the caller that wants to get the results. If the data is binary and the caller is a PID, then I split the lines. I get that many workers as a variable. And then I call concurrency Fount and get the PIDs for that many plus 1, because I've got the collector and all the workers. They all look the same, but you're going to use different parts of the receive loop. Then I send a message to the collector. You need to collect 10 results. Up here, I asked for 11 workers, but I told the collector, when you're collecting, you'll know you're done when you get 10 up. This is the formatter. When a worker gets a message, format, at this position, this was the address, here's the line of data, and that's the collector that you're going to communicate to. And all I do is format the address, format the line as hex, send a collect message to the collector. And I give it my PID so that when I print out the table, you'll get a hex dump, and you can see that there's different PID numbers for each of the workers. Just as an example, so that you know that each line actually was touched by a different process. It's a good example that you can work through and then understand how to use yourself if you made a different style graph or something. And then the collector just collects them. I used an array. I used really tricky Erlang. I've got 10 workers. I allocate a new array with 10 slots in it. And as I get a message back, I insert it into the array. It's already sorted, pigeonhole sort. You have to sort it. You're using concurrency. You can't assume anything comes in order. If you do assume it comes in order, you're shoving it through a gen server and serializing it, and you just defeated all the concurrency. And so then you get a result that looks like this. And here's the memory locations, the hex for each line, the old-fashioned Unix style, and here's separate PID numbers for each one that handled. And you see this only had to handle one character. So it probably came back first, right? So in conclusion, the worker pools are really great as a generic reuse processes, but the overload leads to lost tasks, complicated queuing. There's a hierarchy and bottlenecks with supervisors that lead to catastrophic failure. And catastrophic is a mess in a production system. There is really no back pressure, or it's not intrinsic, and it's hard to add it to a pool. You'd have to put it in the queue or something, and then some protocol for how you back off, and it gets messy. But with concurrency Fount, rather than adding control mechanisms to communicate back pressure and things like that, the reservoir itself is the limiter. Once you drain the pool, you're done. You can't swim anymore. And there's no need to check a count or have a supervisor do something. It's the physical presence of processes in the reservoir is a sufficient data structure. This is a key feature of advanced or beyond advanced Master Jedi level Erlang is partition your architecture using processes and let the process itself be a token that represents a computable state. If the process is there, then that element of the computation is there. If it's not there, it's not part of the computation. In your application, you can freely combine concurrency Founts, multiple concurrency Founts. You could pick PIDs. I could have made a Fount for the formatter and a Fount for the loader and a Fount for the collector and then pull them independently. When you're doing a graph, it's kind of efficient to just get as many PIDs as you need and then wire them all up, maybe by sending a message from one to the other. And that message channel is stored internal to the process. And now the graph is represented by the presence of graph nodes. and the edges are inside the graph nodes, inside the process. And the process architecture is a data structure. That's Jedi level architecture in Erlang. Simplicity in the mechanism is what really removes the bottlenecks and the hierarchy. But the key to making it work is the pace regulation. That back pressure is fundamentally built in. It's not something you strap on after the fact, and it doesn't add overhead. It's fundamental to the mechanism and the way it works. Any questions? So the question is, can you have a remote worker pool? So the first question is, can I have remote PIDs inside a local worker pool, right? I could do it on a slab basis. If I replace start PID with something that round robins to nodes, every slab could be on a different node. So then I can use that as a load balancing mechanism, and I didn't add anything. That's Jedi level, right? I have a reservoir. My reservoir has got salt water. Your reservoir has just got fresh water in it. But you could have remote founts, just like you can have a remote gen server. It's an OTP gen server or gen FSM, so it's no different. You would want the spawns to somehow be efficient and not have your messaging copying lots of data across the network transparently, so that, you know, if you write your code bad, it might incur a lot of message copying. But there's nothing to prevent that architecture style.
Let's say you have a remote database and there's some latency. And so to improve throughput, you'd like to do pipeline.
Right.
I've struggled with this before. With Mobile, for example, like I tried other approaches as well. Let's say you want to keep a maximum of 5 non-responded queries that you see in flight, but at the same time you want to evenly distribute those queries in the workers.
Right.
So
the
worker with 3 inbound, outbound queries, and another with 5, one with 3. Both balanced.
So the question is, dealing with a database, trying to get efficient pipelining or other mechanism of interacting with the database. Nothing about concurrency fount is intended to constrain your architecture. That's the first thing. Second thing is, remember, use processes to partition your architecture. So if you want 5 in-flight queries to the database, you could pipeline 5, but now they're sort of in the same pipe. Because we have this pre-spawned init, I could make 5 connections to the database early when there's no request. And so the process is already idle with a socket connection to the database. It's just waiting for a query. As soon as you send it a message, it forwards it to the database. And then you handle the concurrency in the processes. You would need to manage the number of processes in your reservoir carefully in that case. And you still have the issue of long queries that maybe do joins and other queries that don't. So just like in a worker pool where you have short workers, medium workers, and heavy workers, you might have 3 reservoirs and choose that. But it comes down to partition using reservoirs, then partition using PIDs, then partition using graphs, partition using sockets. You take your architecture and partition it down in an efficient data flow organization, and then you'll get a solution that works. And you can trace it through the system because the PIDs can reflect to gen events, and you can just be observing the flow as it happens. Yeah. If you want to, so the question is, if when you're load balancing to a database, whether you pay attention to the sockets and how they're distributed, or whether you pay attention to the PIDs, I say look at Elysium on DuoMark GitHub. It round robins to the Cassandra. It skips nodes that don't respond, and it has built-in stochastic decay. So every 5 minutes or so, the sockets reconnect, and then they reconnect somewhere else, and it just routes itself around problem nodes, and it load balances through stochastic dynamic traffic. And that's, now I don't implement any logic. I just say, use this one for a while and then quit and use a different one for a while, and everything else works itself out. We turned it on, ran it for a weekend, and said, it stayed up all weekend. And DevOps said, you know, you only had 3 out of 5 nodes running. The other 2 were down all weekend. Oh my gosh, wait a minute. We didn't know. That's great. We had no idea that the nodes were down.
Do you plan to add a call API? Because everything is about events that you are receiving on that.
Well,
More away like this.
so the question is there an API or a way to interface with other libraries or something? You implement the behavior to start a PID and init the PID with a state. So if there's an API that requires a token or something, put that in the init state. Every time you spawn a PID, you just get a copy of it. So on spawn, I'm actually messaging. This is another Jedi Erlang trick that you probably use and you don't know you use. How to send a message without sending. Spawn a process that's using a variable from your process. It has to get copied into the new process space, and now you just effectively did a message without sending a message. It's actually more efficient because it's copying the process memory at spawn time. So in the start PID behavior implementation, you would then initialize the API. And even if it takes 30 seconds, you make a deep reservoir, you do the initialization, it takes all that time, and now when you grab a PID, it's ready to go, and there's no latency. There is a bunch of upfront cost, and it may cost memory and other things, and you have to balance off. Nothing's magic. You're just trading latency for memory, latency for pre-CPU. So you're balancing out when the spike causes the storm of CPU and memory. Yeah. Yeah, but what I don't want is, so the question is, why do we drop workers after they're pulled from the reservoir and used once? Why do we do one-shot usage? Oh. Oh. So the question is, I understand why you let them go because you don't want the serial bottleneck of putting them back. Can I reuse them? I wouldn't put them back into the reservoir. I would just keep them. Like, as soon as you get a PID from the reservoir, it's yours. You own it. It's the application. The application could register it in ETS and keep it around for 5 minutes or whatever. Inside epoxy, there's a concurrency cache. You could stick it in the cache and have it expire after 5 minutes or something. But it's yours to manage. The reservoir only wants to pace how quickly you spawn and pre-amortize the cost of spawning. That's really all that it's doing. It's not managing processes or letting you reuse processes. It's just pacing and pre-amortizing the latency cost. So you would build a second mechanism and a different technique for holding long-term PIDs. Right. So the question is, using this technique of connecting to a database and having a fresh socket every time you spawn a fresh PID. In this case, the PID is a constraint on how much concurrency and sockets you're placing on the database. The socket is really the resource that's controlled. It's better to take the socket, put that into ETS, and when you spawn a PID, grab the socket for ETS, and don't let one process own the socket. You can pass the socket around. It's only if you're using active sockets that you need to be the owner of the socket. Jedi trick number 4, right? If you have a socket that somebody's open to you, anybody can write to it. So you can have multiple concurrent processes sending data. It'll be interleaved, so you got to be careful about that. But when I'm done with the socket, and I know I'm done, I can give it to another PID, and they can use it again. So when you have lots of data to communicate to a database, move the socket to the data. Don't move the data to the socket. Jedi trick number 5. I think there's a lightning talk in there somewhere.
Thank you.
Okay.
And yeah.